We often assume learning to pilot an aircraft is essentially a specialized form of driving. Push a pedal to accelerate, turn a wheel to change direction. But the Federal Aviation Administration considers this analogy misleading. Unlike a car, tethered to a two-dimensional road, an aircraft operates within a three-dimensional fluid environment. Mastering this environment requires coordinated manipulation of three spatial axes: pitch, roll, and yaw. Cockpit inputs physically map to aerodynamic control surfaces. The yoke moves elevators and ailerons for pitch and roll, while floor pedals deflect the rudder to control yaw. Total mastery of these inputs is the ultimate objective of flight training, a concept known as airmanship. Airmanship is a measurable set of skills: subconscious muscular coordination, precise timing during maneuvers, and an intuitive sense of airspeed. The most critical, physical component of this skill is control touch. This is the ability to sense the aircraft's attitude and the aerodynamic forces acting on it through the varying physical resistance transmitted directly through the flight controls. In early, lightweight aircraft, this touch was a direct physical struggle, a literal battle against the wind hitting the wings and tail. As aircraft evolved in size and speed, engineers were forced to sever this direct mechanical link to protect pilots from the massive aerodynamic loads involved. This created a new engineering challenge: the need to artificially synthesize a physical control touch that is no longer naturally present. Without this engineered feedback loop, the human brain cannot process the aerodynamic reality of high-speed flight, a disconnect that can make even the most advanced aircraft difficult to control. To understand how this works, we have to look at the baseline mechanics of a standard training aircraft. When the pilot pushes the yoke, motion travels through push rods and cables to deflect the elevator. Airflow strikes the surface, generating immediate aerodynamic resistance. This force translates backward into the yoke, letting the pilot feel the unadulterated weight of the wind against the airframe. This one-to-one mechanical ratio is ideal for small planes, but it creates a crisis as airframes grow larger and faster. This chart shows the formula for dynamic pressure. Doubling an aircraft's airspeed quadruples the aerodynamic resistance on its control surfaces. Since dynamic pressure increases with the square of velocity, the load on the controls can quickly exceed the limits of human muscular strength. Early engineers tried to solve this with complex gearing systems, attempting to provide pilots with a mechanical advantage. They also developed servo taps, small hinged surfaces that use local airflow to help push the massive primary control surfaces into position. Eventually, these mechanical workarounds reached their limit. The physics of high-speed flight simply outmatched human muscle. High-performance and supersonic aircraft, like the SR-71, required a fundamental architectural shift. To manage massive aerodynamic loads, designers moved to hydromechanical flight control systems. This architecture has two halves. The mechanical circuit is initiated by the pilot, while a separate hydraulic circuit performs the physical work. The pilot's input only opens a servo valve, and high-pressure fluid forces the actuator to move the control surface against the wind. While this solves the power problem, it has a dangerous side effect. It has severed the physical feedback loop. Because the hydraulic actuator absorbs all the air resistance, the pilot feels zero resistance at the yoke. Without physical resistance, a pilot lacks control touch. They can easily overstress and destroy the airframe by moving controls too aggressively for their airspeed. To prevent this, engineers developed artificial feel devices. Baseline systems use springs to artificially increase resistance the further the yoke is deflected from the center. Advanced systems, like those found in the F-8 Crusader, require dynamic feedback provided by a bob weight. This weight is linked to the pitch axis of the control stick. As the aircraft pulls G-force, the bob weight pulls down, scaling the resistance the pilot feels to the actual acceleration of the aircraft. Pilots are also warned through devices like the stick shaker, which vibrates the control column to communicate when the aircraft reaches aerodynamic stall limits. Modern aviation relies on these complex mechanical systems for the sole purpose of providing synthetic tactile feedback to the pilot's hands. In advanced modern aircraft, manual mechanical linkages between the cockpit and the wings have been eliminated. Through fly-by-wire and power-by-wire systems, cockpit inputs are converted into digital electronic signals. These signals are processed by central flight control computers, which then command self-contained electro-hydraulic actuators to move the control surfaces. This total digital abstraction is the standard for modern combat platforms like the F-35. Despite removing physical cables, these computers are still programmed to synthesize resistance at the pilot's stick. Tactile feedback remains a biological requirement for the human brain to maintain control touch. We are now moving toward a future of experimental flight control called active flow control. This technology replaces moving flaps with compressed air slots. Emitting small jets of air invisibly alters the flight path without any hinged surfaces. There is a vast technological gap between the mechanical pulleys of a training plane and the abstract interface of a morphing wing jet. But after more than a century of aviation, the core biological loop of airmanship remains unchanged. True airmanship is the precise translation of human intent into three-dimensional aerodynamic reality, regardless of the technology sitting between the pilot and the wind.